going to start chapter 12, and chapter 12 is all about a very important calculus concept called limits. We actually talked about limits at the beginning of chapter 1, and we briefly touched on them, but now we're going to go back and get them in more depth. So we're going to review two basic problems, maybe to jog your memory of what limits might have looked like, and then we're going to go more deep into today, finding the limits of a function at a point. So for problem number 1, as we look into this, what I'm going to do is I'm going to read it to you and show you some of the notation as we have here. So here is how question number 1 reads. 1, evaluate the limit as x goes to 7 of 4x plus 1. And then you know what, I just realized this, looking at this, is supposed to be a negative 7. So we'll change this to a negative. I think I changed it on your notes, so it should say a negative 7. So the limit as x goes to negative 7 of the function 4x plus 1. So a little bit of background information on functions. Functions are always going to be, or on limits, the limit is always going to be an extra descriptor that we have of a function. And so the function specifically is represented by its equation, so it always comes after. And then the limit is asking us to evaluate what is happening for the y value of the function at a specific point of our choosing. Or later we'll see other types of limits, but today we're just focusing on points. So we're saying for the function 4x plus 1, what is the y value? What is the graph doing? Where is it located at x equals negative 7, or as x gets close to negative 7? So there's two ways we're going to look at this. We're going to look at the graph and we're going to look at the table. So basically, here's how we do this. So we go to the x value of negative 7, and then we head to our graph. And then we look at where we are at on this graph. And this clues us in. So at negative 7, it looks like the graph is at this dot here. And the value is going to be negative 27. What you want to think about is as I travel on the right, so as I get closer and closer, negative 6, negative 6.5, that y value looks like it's getting closer to negative 27. As I come from the other direction, I'm at negative 9. I pass x is negative 8. I get close. Again, we're back at that y value of negative 27. Looking at the table, we can see analytically with these numbers, we have a negative 27, a 0.04, negative 27.004, and we're going to leave this blank open because we're figuring that out, but it looks like on either side we just pass exactly through negative 27. So then our conclusion here is that the limit as x goes to 7 of 4x plus 1 is going to be negative 27. In this case, the limit ended up being the y coordinate of the point for our function 4x plus 1 at negative 7. Okay, now let's look at number 2. Another limit. Let's pay attention first to, we have the function here. It says evaluate the limit as x goes to 4. So we're going to be looking at our graph at the x value of 4, looking at the y value of x squared minus 16 all over x minus 4. All right, so most simple way to do it. Go to x equals 4. Let's count over 1, 2, 3, 4. Let's go up. And that situates us right here on the graph, which looks like a y value of, and it looks like it's going by 2s. 2, 4, 6, looks like that's a y value of positive 8. But we have a hole here. There is an open space on the graph. So that makes us think maybe this does not exist. But as I approach and I get really, really close to this hole, as I look at my table, this number is getting closer and closer and closer to 8. As I come from the other direction, I'm going to, again, get smaller and smaller, but closer and closer to 8. And that's happening as well as I approach 4 from the other side. So our conclusion is that although there is a hole there, the graph is heading toward the value of 8. So on either side, it's getting closer to 8. So we can conclude that although there is a hole exactly at 8, the trend is as I get as close as possible as I can on either side, we're going to be right at 8. So the limit of this function is equal to 8. So basics on limits here is that the limit of a function at a point C is going to be some unique y value that the graph approaches as x approaches c from the left and from the right. So we're going to look as I convert, we call this, I wish I could do this in person, because what happens is I think about if I were to trace my pencil route from pick up my two of my fingers or two pencils and trace the graph closer and closer from either side as shown by my arrows, we're going to end up right on, we hopefully will end up right on close to the same number for as we go from either side. So let's look at a couple of properties here in our notes of limits. Now that we've seen kind of basically how to do this as we look. So really to summarize, there will be a couple exceptions we'll talk about, but it will most likely be if the graph passes through a point, whole or not, it is going to be the y value at that point. So here are some rules. First thing is that this is really important when it goes to what we just saw. The limit of a function f of x as x approaches c. So the limit at c does not depend on the actual value of the function at point c. Here are some examples. What we just saw is if I look at the point C and I go to my graph and there is a hole, the limit actually does exist at the hole. So even though there is a hole, the limit exists at that point because the graph on either side is heading toward the same number, and we're going to call that number L. But if we notice, the function is undefined at that point. It doesn't matter if the function is undefined at the point as long as we are approaching that same point from either side. Let's look at another one. For this function here at c, we have a hole again, but they actually gave us a defined dot. So it means that the function is actually defined at c. It has an actual value, and they're going to tell us that it's equal to this value n, but the limit still exists, and it's that value of L that we pass through when we pass through the hole. Or we have a basic example over here with a common limit where there is no hole, and we pass through the value. So the limit and the function have the same value. So if the graph passes smoothly through the point that you're looking for your limit, hole or not, it is going to be the value it passes through at that point if it goes through smooth. And we'll look at a couple of exceptions. Okay, so then next up, the next type of limit idea that we have is called one-sided limits. There are a lot of text here, so we're going to work kind of piece by piece. So one-sided limit is the number we get when we approach a function from the left side or the right side. So for a left-hand limit, I'm going to read you off some pieces, and then there's some important notation that we'll talk about. So if the value of a function approaches a unique number from the left, so what you would do is you would take your graph. Let's say this is our graph. And let's say that I am trying to, this is where C is. So we'll be somewhere here. The left-sided limit is as I jump to the left side, so somewhere over here, and I make a smooth path following it towards that point. As I get there on the left side, what number am I at? So if the value approaches a unique number from the left, we'll call this number L1, then the limit, this is our notation here. I'm going to just show you, you can read through it all, and here's the really key thing that I want you to look at. This minus sign above the C means this is a left-handed limit. And here's how this reads. I wrote this out below. So this notation right here reads below, the limit of f of x as x approaches c from the left is equal to L1. So we're going to say that, oops, it froze on me here. We're going to say this value is L1. Okay. Right-handed limits is really going to be the same idea, but we're going to switch out some notation. If the value of a function approaches a unique number L2 from the right, and so now we're going to say that this number this time will be L2 as we approach it from the right, then our notation is as follows. This is what it looks like for a right-handed limit, and instead of a minus, we have a plus, and this means this is a right-handed limit. We go to the right of the c value we're looking at, we approach, and then we give the answer of the y value we're going towards. So the limit of f of x as x approaches c from the right is L2. These numbers can either be the same or they can be different. So in the example that I just gave, this would be the same. From the left and the right, they're heading toward this common point in the middle. As a quick sketch, a point where they might not be the same would be a piecewise function. So if I gave you, hold on just a second, we're having some technical issues. Okay. So if I were to draw a function and give you a point here that we'll call this the x value of c, let's say that the graph goes like this. It's a straight line, we have a circle, and then maybe there's a dot, and then maybe it goes and it curves this direction. So at c, my function is one of two different places. There's an open circle and there's a closed circle. As I approach from the left, if I were to jump to the left, that would be including all the regions of the straight part of this graph. And as I go from the left, when I get to C, let's say this is a y value of 2, we'll call this 4, then the left-handed limit is approaching a y value of 2. But if I were to follow the graph from the right, when I get to C, on the right, we are at 4. And so this would be a case where the left and right-handed limits would be different. All right, this is all leading up to the most important part of these notes, which is going to be the existence of a two-sided limit at a point. So I believe your notes should have this. For some reason, mine don't. This should say the existence of a two-sided limit. And this is just what we think of as a regular limit. Here's our definition. The limit of a function f of x as x approaches c exists if and only if both one-sided limits exist, so the left limit has to exist and the right limit has to exist, and they equal the same number. Written out in notation, it looks like this. If the limit as x goes to c from the left, that's what the minus means, of our function f of x is equal to the limit as x approaches c from the right of f of x, and it equals some number, we'll call that number L, then that means the limit, the two-sided limit exists, and so then we could write that the limit as x goes to c in general. So we don't have to put a left or a right on it anymore. We can just say the limit as x goes to c of our function f of x is equal to L. So now let's look at some examples of some left and right-handed limits from graphs. We're mainly going to work today using graphs. We'll talk about using equations more as we go. And limits that exist at a point based on this two-sided limit and some limits that don't exist. So we're going to use Desmos for this. For the ease of this, I've already taken a screenshot, but I'm going to show you how to do all of this. So what we're going to do is we're going to graph the function in Desmos. So we're only going to use the graph for this. If you don't have a graph when you go to do your practice, you're going to have a difficult time. So please make sure you get a graph. Take a screenshot, put in your notes, and then find each one and two-sided limits. So looking at these different functions, if you look at number 4, hopefully you can figure out how to type that in. But number 3, it's been a while since we've typed. This is, remember, a piecewise function where they're saying any place on the graph where x is less than 1, we're going to follow this curve. Wherever x is greater than 1, we're going to follow this second curve. So I'm going to show you how to type those into Desmos. Okay, so what we need to do, let me clear out this old one. What we're going to need to do is, one, we're going to have two different lines for this graph. So the first thing is, let's say our first one is y equals 1 minus x squared. You actually could leave off the y equals, just type in 1 minus x squared. Okay, now I want to type in the x is less than 1 part. What we're going to do is our bounds, that x less than 1, those are our restrictions, we're going to put those in brackets. So if you click ABC, if you look along the bottom row, there are squirrely brackets. You can just click that once and it pulls up your brackets. Go back to the home page and we're going to type x less than 1. And that should be it. And what you can see is it cut it off. Great. Okay. And then for the next one, we're going to do y equals negative x minus 1. We're going to have brackets, and then we want x to be greater than 1. All right, awesome. And then that's our graph. That's all we need. So then if you want to pause and take a screenshot of this and put this in your notes, because I believe yours don't have them, I've already screenshotted. And if you want to ever change the color, just as a quick note, because I think mine are blue and red, they don't have to match, but you click the settings gear up on the top right of the equation type in, and then if you just click the circle, it will bring up the dot, the green dot. It will bring up options to change the color or make it dotted. Okay, so now let's look at this. So this is our graph. One thing is there's always, if we have a piecewise function, we're always going to have one open circle and one closed. Remember that it's the equal sign that determines it. So x less than 1, that means we can't exactly equal 1. So that red graph, everything less than 1, we're going to put an open circle here, and then we're going to add in a closed circle. So Desmos can't show us this, so we have to take what we know about piecewise functions, and then remember this does go on infinitely, so we'll add arrows. Okay, so now what we're going to do is we're going to follow our limits, and so the first one says the limit as x goes to 0 from the left. So we have a minus sign, so that's the left. So what you want to do is we're at 0. You want to hop to the left side of it, so anywhere in those negative numbers. We're going to trace towards it, and then right when we hit 0 from the left, it looks like our y value is 1. So the limit from the left is going to be 1. Now let's go from the right. So we take 0 as our endpoint, hop a little bit to the right, trace towards it. It looks like we also end up at a y value of 1. This might almost seem confusing because it's simple, which is what sometimes makes it confusing. So from the left and the right, I take both of my fingers, I can trace from both sides, and I hit the same point. I hit a y value of 1. And what this means for us here is that because from the left and the right, the limit both equaled a number and it was the same number, that means that in general, we can remove those plus and minus signs. The limit as x goes to 0 of f of x is 1. So that is a two-sided limit that exists. Let's do another one. So now, the place where our piecewise function breaks is at 1, and this will be interesting to look at what happens here. So as I approach 1 from the left, I'm going to now erase these arrows. As I approach 1 from the left, here's 1. We want to make sure we hop a little bit to the left and head down until we hit x equals 1. It looks like at that point the y value is a y value of, let me get these colors to match, it's a y value of 0. So the function is at 0 as I approach from the left. As I approach from the right, I trace my graph, and when I hit the x value of 1 on this graph, I am at a y value of -2. So I am at a y value of -2. So as I look, as x approaches 1 from the left, and as x approaches, or as our limit approaches 1 from the left and from the right, we're actually ending up at different spots. And so in that case, what that means that we can conclude is that this limit as x goes to 1 does not exist. And at 1, this is a classic case of a limit that doesn't exist. It's this idea of if the graph does not smoothly pass through a point, if there is a jump, the limit's not going to exist. So there's a jump here, which means this limit does not exist. So we have one more example that will conclude our notes for us here. So let's look at this last example. So for this one, in case you need some help with Desmos, I'll show you how to type it in, but I also already have this screenshot. So you can X out the graphs that you had before. So we want the absolute value. So at this point, the absolute value button is right above the ABC button on the left. And then we're going to type in x minus 2. And then if you click outside, if you just arrow outside of the absolute value, you can click the divide button. It will give you a fraction bar, and then x squared minus 4. And again, like mine gave it in black. I don't love that. If I didn't already have a screenshot, I would have changed it, but it's up to you. So this is a very funky graph. There's some weird things happening at 2. So take a screenshot, put it in your notes. And now let's look at this. A couple of limits. So we're again going to look at the limit as zero. So we're just going to look at what's happening with our graph from the left and from the right. So the first one, part A, limit as x goes to 0 from the left of our function. So again, we want to head toward the the x value of 0 from the left. And it looks like as we approach it, we're hitting, looks like that's right, between 0 and -1. So we're going to be at -1/2 from the left. And then as we go from the right, then we're also hitting the same point. So we're also at -1/2. So this is that point, which is our most common limit that exists, where the graph passes smoothly through the point. We identify its y value. The left and right limit equal the same thing, so that the limit is two-sided as x goes to 0 for the function f of x, and it equals -1/2. So for the next ones, we're going to look at the limit as x goes to -2 from the left. So it looks like at -2, we actually have a vertical asymptote. So from the left and from the right, we have an asymptote because it can't equal that number. And so it's passing infinitely there. And so as I approach from the left, this one's going to be interesting to trace. I get closer and closer. I get to -2.5, -2.25, and the closer I get, the further up we're going. And so as I get closer and closer, we can imagine that this value is going to skyrocket toward infinity. And so this would be a limit where the actual value that we'll put down is, we'll say this is actually going to positive infinity. As I get closer and closer to 2, the value will just get larger and larger. As I look from the right side, I follow my graph, maybe start at 0, and then it shoots downward toward negative infinity. It keeps growing, and it keeps growing as we get inch closer and closer to -2 from the right. So this would equal negative infinity from the right. And so here, for one thing, the limit from the left and from the right, these don't equal numbers. And so in that case, they don't exist or they go to infinity, they go to negative infinity. So those aren't going to numbers. And then and they're also going to different infinities. One is going to positive infinity, one is going to negative. So there's multiple reasons why we could say the limit at -2 does not exist. And if we talked about, if you remember going back to make the connection to our types of discontinuities that we had, this is that infinite discontinuity at -2 because it's going up to infinity. All right, last one on our notes for the day. Let's look at the weird gap that we have happening at +2. So at +2, looks like we are going to have 2 open circles, because if we look at the denominator, x cannot equal +2 because it would make the denominator equal 0. From the left, it looks like we are approaching this negative y value. If you're not exactly sure, go to Desmos and examine the graph. If we look, it's going to -1/4. So from the left, this graph is heading toward -1/4, or you might see that as -0.25. As we go from the right side, we're above 0 a little bit, and it looks like we're going to the same point but just positive, and so this would be positive 0.25. So they're going to a similar value, but just one is positive and one is negative. But because of this jump gap, because the left and the right side limits are going to different numbers, we can conclude that this limit does not exist. So that's the end of our notes for this video. On the next page, I've given a couple of extra examples that in the guided notes, will put the answers to. So if you want to look at those as you finish, you can look at those answers in the guided notes. Otherwise, from here, we have the practice for 12.1 day 1. And then once you finish that section, the next part B of today's assignment will be to look at 12.1 day 2 video and practice as well.